Okay, for exercise 6.14, slightly different. It asks us to find a vector equation of the line that is common to the planes r dot 2i plus 5j plus 2k equals 5 and r dot 6i minus j minus 2k equals 7. Okay, remember r represents an arbitrary x, y, z vector whose endpoint is inside the plane. So another way to write these two planes is simply 2x plus 5y plus 2k, whoops, that's not right, 2z is equal to 5, and 6x plus 5, what am I doing? 6x minus y minus 2z is equal to 7. So clearly their normal vectors are not multiples of one another, so they're not parallel. And so if we do draw them, let's suppose that one of them looks like this, and the other one looks like this, and intercepts it along that line there. Alright, so what we actually need is 2 points along the line of interception. And then as soon as we got those 2 points, it's very easy to find the vector equation of the line. If this is the point A, and this is the point B, then the vector equation of the line L that goes through AB is simply R of T is equal to OA plus T times AB. So we have to find points A and B along that line of interception. And note that any 2 points A and B will do. Now A and B, because they're along the line of interception of the planes, that means they're in both planes. So that means they make this equation true and they make this equation true. And it doesn't matter what what point A and what point B we choose, we can still get the vector equation, or get our vector equation of the line using the 2 points that we find. So you can find them like this. Just set, well, choose one of the coordinates, doesn't matter which one. I'm going to choose x, and I'm going to say let x equal 0. Then if x equals 0, we have that 5y plus 2z equals 5, and minus y minus 2z equals 7. So we can find y and z by simply adding these two equations together. And so, again, we're just looking at this part here. So adding those together, we get 5y minus y is 4y, and then 2z minus 2z is 0. So 4y is equal to 7 plus 5, which is 12. And so we have that y is equal to 3. And if y is equal to 3, then x is equal to 0. And so we have negative 3 minus 2z is equal to 7. And so that means that minus 2z is equal to 7 plus 3, which is 10. And so z is equal to minus 5. So that means that our vector OA can be 0, 3, and negative 5. No problem. This time let's find another point B by letting y equal to 0. And if y equals 0, we have 2x plus 2z is equal to 5, and 6x minus 2z is equal to 7. And so adding those two equations together, we get 8x is equal to 12, and so x is equal to 1.5. And if x equals 1.5, then 3 plus 2z equals 5, so z equals 2. And so our vector OB can be 1.502. And now we're ready to get a vector equation of our line L, because we know that the vector AB, which is equal to OB minus OA, so 1.5 minus 0 is 1.5, 0 minus 3 is negative 3, and 2 minus negative 5 is 7. So that means that the vector equation of our line L is R equals OA, which is 0, 3, negative 5, plus T times AB, so 1.5, negative 3, and 7. And that's all for that question.